Hey everybody, Craig here, back with a late arrival video for your CT6 work. I have a spreadsheet I've prepared. I'll give you that in a second video. I do my work much like your author does. We'll talk about that a little bit later, but first I'd like to talk in generalities. Let's talk about confidence intervals. Before we get there, let's first let's take a different tack. Let's assume that we have a normally distributed population. And we've learned that normally distributed populations happen quite often. Nature gives us a lot of them. The height of people, the diameter of trees, the weight of ants, and they also come up in many other places. In economics, a lot of things are distributed normally. What do we know about the normal distribution? Well, we know several things. One of the most important ones was that the mean, the median, and the mode are all equal. And if this is a population, we know what the true valuation of the population mean is. And we use this symbol mu, mu. But let's now say that we drew samples from the population. And we calculated some averages from those samples. Well, first of all, let's say that the true value of the mean, is equal to 10. But now I drew several samples from the population, and one mean I got was 12, and another one I got was 8, and another I got was 6. Now, what we're going to learn to do is calculate confidence intervals. And what they are is they put a range around these means that we calculate from our sample. So the one around 12 might be that big, ranging from, I don't know, somewhere like 8 up to 16. And let's see, this one might be that big, and this one might be that big. Whoopsie, they should be even size. Okay? We're going to learn how to calculate those confidence intervals, and we're also going to put a degree of confidence with those confidence intervals we create. For example, let's say, assume that this one is the 95% confidence interval. Well, that means we're 95% confident that the true value of the population mean falls within that range. Well, in each of these, it looks like the mean falls in. Oh, but not the third one. We don't always get it right. Perhaps, we're confident that 95% of the time we're going to catch the true value of the population mean in our confidence interval, but we don't always do it. Let's see, that's 1 out of 20 times. We don't. Okay, what if we increase the confidence level? Let's say we want to be 99% confident. Well, when we calculate our confidence interval, what that's going to do is push it out. Yes, if we want to be more confident, we're going to end up with a wider confidence interval. Okay, let's talk about how we're going to create these confidence intervals. First of all, let's just do this. First of all, it depends whether we know information about the population or if we only have information about a sample. So, if sigma, which is the population standard deviation, if that's known, we have an equation that we will use. And what does that equation look like? It looks like this. The confidence interval will be the value of the sample mean that we calculate, plus or minus something called the z-statistic. And we learned about that, I believe, in chapter 6, 5, something like that. times the population standard deviation divided by the square root of n, where n is the number of is the sample size. I'm sorry. Okay. Now, how often does this happen? How often does it happen that we know the standard deviation of the population? Not very often. Let's see. Sometimes in industries, if you have a machine that you've used for 20, 30 years, and you know it makes parts that are exactly this size, you might know the standard deviation. When else? Not many times. There's very few examples. And so what we end up doing is calculating a confidence interval using S, the sample standard deviation. Or, wait a second, let me back up. Let's say, yes, where the population standard deviation is unknown, then we use S, the sample standard deviation. And our confidence interval looks a little different. Again, we'll have x bar plus or minus something we're going to learn about called the t statistic. It's like the z statistic, but it's a little bit more conservative. We don't know as much about the population, so we have a value called t that is a little bit more conservative, not as liberal as the z statistic. Okay, so x bar plus or minus t times, it looks similar now, times S, sample standard deviation, divided by sample size. That is how we are going to calculate our population, big difference, whether we know the population standard deviation. We will be using this case a lot because it's going to be very rare that we know the population standard deviation, and so we will use this version of the formula. There's one other thing we're going to do, and that is to calculate the confidence interval on a proportion. And I just lost my page here. Give me a second. Where'd you go? There. Oh, staring right at it. So this will be the confidence interval on a proportion. And we're going to, whoopsie, fell off the map there. There we go. We're going to use an equation. P is going to be our sample proportion. And the equation that we will use for the confidence interval is going to be that sample proportion plus or minus our z statistic times the proportion times 1 minus the proportion divided by sample size. All of that's under the radical. Now, it might have made a little bit sense when I said when we know the sample standard deviation, we're going to use the z statistic, which is a little bit more liberal. It'll give us a little bit tighter confidence intervals. But when we only have a sample, we're going to use the t statistic, which is a little bit more conservative and going to give us slightly wider confidence intervals. Why then does our proportion go back to the z statistic, even though we're going to use this when we draw samples? Well, it's just because the statisticians can show that proportions are much more like a normal distribution than they are a t-distribution. The z statistic, which comes from the normal distribution, works much better. Okay. Let's see, what else do I want to say? I want to first point out z-values and where we're going to get those. Z-values, there is a table on page 359 in your text. And when we're calculating confidence intervals for where the standard deviation is known or for our sample proportions, there are some common z-values that we use all the time, and I'll just replicate what's in our text. These three are very commonly used. And what we have to do is, if we're looking for a 95% confidence interval, we have to find an alpha level. And alpha we define as 1 minus the confidence level. So it would be 1 minus 0.95 or 0.05. And let's see, so the 90 would be the 0.1, 95, 0.05, and 99, 0.01. Now, because the z distribution is a one-tailed distribution, we need to take 1/2 of these values of alpha when we look things up. And so we often talk about the alpha over 2 value. And so then we're going to get slightly different values, just taking 1/2 of each of these. Okay, and finally, what is that z-value associated with alpha over 2? Well, 90%, it's 1.645 and 1.960 for the 95% confidence interval, and 2.576. Again, these are in table 8.1. And we'll be using ones. We'll use this 1.96 quite a bit. Okay. Let's leave it there. I'm going to jump over to my spreadsheet. We'll pick it up there.